Now this right here is a little bit of enzymes in a nutshell. We're going to come back to this whenever we discuss enzymes, which I believe would be chapter 3 material. Energy coupling, though, is the concept of chemical coupling of exergonic and endergonic reactions to allow otherwise unfavorable reactions to take place. The high energy molecule ATP reacts directly with a metabolite that needs activation. So this right here is our molecule adenosine triphosphate, or ATP. We've got, and I'm just going to do a little demonstration, not demonstration, but I'm going to highlight some of those different things. We've got our ribose, we have our nitrogenous base, or adenine, and then we have our 1, 2, 3 phosphates. These are known as our alpha, beta, and our gamma phosphates. So removal and hydrolysis of that beta gamma phosphate bond releases a large amount of energy. And that is something that you can couple with another reaction. Okay, our chemical example here is we're talking about the enzyme hexokinase. So I'm going to write that over here. Hexokinase. Now, hexokinase is the first reaction in the breakdown of glucose. Hexokinase will catalyze a reaction taking glucose and pi, also known as inorganic phosphate, and it will produce glucose 6-phosphate. Now, this free energy diagram that we see here shows our reaction coordinate and the free energy of this reaction. So what we've got is a low free energy to a higher free energy. So this is going to go from, let's just say 0 to, oh, that's not even a remotely straight line, from 0 to a significantly higher number there. So this is going to make something that is, well, it's going to take energy input to get to that next level. Now, our second reaction. Our second reaction here is listed as ATP yields ADP and pi. Now, what this shows is that our starting molecule, ATP, is a higher energy molecule than our product. So reactant, product. That's supposed to say product. My tablet's a little bit screwy. So this is taking something that's high energy and producing something that's at significantly lower energy compared to reaction number 1, where we have our starting compound of glucose and pi at low energy going to a high energy. Okay, so this really does capture energy coupling quite well because it shows glucose plus ATP yields glucose 6-phosphate plus ADP. Okay, so what that displays here is an overall combination of our energy of glucose and ATP. We're at a starting point that is higher than glucose plus pi, and it's lower than ATP. So glucose and ATP have a net that's right here where I'm drawing my little star there. All right, my product, glucose 6-phosphate plus ADP, is lower than our starting point, and we were able to ultimately get to something that's, well, a product that's lower energy than our starting point. So that's a favorable reaction, going from where I have my X to my Y. That's an overall favorable reaction. If we compare reaction 1, which was unfavorable because we go from low to high, reaction 2, high to low, well, reaction 3 is the combination of those different things. Okay, catalysis. A catalyst is a compound that increases the rate of a chemical reaction. Catalysts lower the activation energy, or lower the activation free energy, delta G double dagger. Catalysts do not alter the delta G naught. Okay, so the overall energy change from our, think about this as our products to our reactants. So if we think about a free energy diagram, we're looking at something like this. And if we look at the introduction of an enzyme, That's not drawn particularly well. And on the next slide, we're going to see what it looks like. But enzymatic catalyst offers acceleration under mild conditions compared to a chemical catalyst, high specificity for the substrates, and the possibility of some sort of regulation, whether it's a feedback loop or some sort of out or exterior regulation by another party. Now, here's what I was trying to display in the previous slide by drawing it. Well, I shouldn't have done that, but live and learn. Okay, so what we have here is our reactants A. In the absence of an enzyme is our blue line. We go from A to our activation barrier, our transition state with that double dagger, and then we go all the way down to our products. Now, we introduce an enzyme that catalyzes this specific reaction. So we have an uncatalyzed reaction in the blue line and a catalyzed reaction in the red line. Well, the difference from A to B, that has not changed. This value right here has not changed at all. What has changed is this intermediate step right here. In the enzyme catalyzed reaction, it goes way up here. In the enzyme non-catalyzed reaction, we go way up there. In the enzyme catalyzed reaction, we don't go nearly as high. So it makes that reaction go a little bit faster, or it makes the reaction go without so much energy being utilized.